Hello students, our next topic is energy stored in a capacitor. Now you see, we can give the charge to a capacitor by some battery or potential V. When we are charging the capacitor, the charge during the process of charging, the capacitor plates are going to get the charges, and further keeping the charges will feel the force of repulsion, and we have to do the work in placing more and more charge on the plates. So that work done would be stored in the capacitor as its energy. So now let us find out what the energy is which is stored in the capacitor. Consider two parallel plates having two equal and opposite charges, plus Q and minus Q. And let us consider the charging is being done by the battery with potential V. The process of charging a capacitor is equivalent to transferring charges from one plate to the other of the capacitor. The moment charging starts, there is a potential difference between the plates. Therefore, to transfer charges against the potential difference, some work is to be done, and this work is stored as electrostatic potential energy in the capacitor. So, we have to simply find out the work done in placing the charges, or in how much work is done in transferring the charges from one plate to the other plate. Suppose if dq is the charge which is being transferred from one plate to the another plate against the potential difference V, then work done would be V into dq. And we know that V is charge per unit capacitance. From the basic definition of the capacitance, we can write potential as charge per unit capacitance. Now the total work done or energy transfer charge Q is, so we can integrate this expression to find out the total work done for the charge transfer 0 to Q. So this would be, we know that C here is constant, that is a constant of this arrangement. We can take it out. So Q dQ is the integration. So integration value would be Q square over 2. And when you will substitute these limits, you will get this expression of the energy. Now you see, we are having the basic definition of the capacitance, that is charge per unit voltage. So we can write the same expression in terms of other variables. This can also be written as half CV square, because you see Q is equal to, using this basic definition, C is equal to Q over V. So Q you can replace from here. If Q is being replaced, this can be written as CV square. One C is going to get cancelled. So this way will become C into V square. Here you will get C square V square, C square V square over C. You will get C V square. Or you can replace C from here. You can write C as Q over V. So one Q will get cancelled. So another expression of the energy you will get as energy stored in the capacitor as half Q into V. So all the three expressions are in terms of the different variables. So you can write in this way the total energy stored in the capacitor. Next is energy density. As the name is indicating here, density. Energy density is what? This is the energy per unit volume. So this we are going to substitute. This we are going to find out for parallel plate capacitor. We know that energy stored in parallel plate capacitor is half CV square. But C value is A epsilon naught over D for parallel plates. And V in terms of electric field is E into D. So if you will substitute both the values of C and V here in this expression, C is A epsilon naught over D and V is E into D. you will get this value of the energy stored in the capacitor. Now just see this term, A into D. A is the area between the two plates and D is the distance between the two plates. Area of the two plates and distance between the two plates. So this term is basically the volume occupied by the two plates of the capacitor. So energy per unit volume is what? This is half epsilon E square. So this term we have got is the energy density. So energy density is what? This is half epsilon naught E square. So this is one very important expression we have obtained. So energy density of a parallel plate capacitor is half epsilon naught E square. Epsilon naught is the permittivity of the free space between the two plates of the capacitor. E is the electric field which is existing between the two plates of the capacitor. So what is the SI unit of the energy density? Energy is joule, density is means per unit volume. So the units will become joule per meter cube. So energy density is generalized as energy per unit volume as we have already discussed. Now, energy stored in series combination of the capacitor. Now when we know that when the capacitors are connected in series, how we can find out and what is the value of the net capacitance of the combination. In series combination we know that the reciprocal of net or capacitance is equal to the sum of the reciprocals of all the capacitors. So this formula we have already derived. And we know that, you see, this is 1 over C is equal to 1 over C1, 1 over C2. So it's better to write the expression of the energy density in terms of 1 over C expression. So 1 over C, if you see 1 over C, C here is the equivalent capacitance of the combination when the capacitors are connected in series. So 1 over C can be replaced by 1 over C1 plus 1 over C2 plus 1 over C3 and so on. So you can see we can separate all these terms. So what you will get? Half Q square over C1, half Q square over C2, half Q square over C3 and so on. Means you are going to get the sum of the energies of the individual capacitors. So here you see when all the capacitors are connected in series, then the net net energy stored would be the sum of individual energy of all the capacitors. And how this energy is going to get changed in parallel combination of the capacitors? In parallel combination, we know that the energy, the capacitance, the net capacitance is the sum of all the capacitances. So again, we can write the expression of the energy in terms of C only. So this expression we can use here, and in parallel combination we know that the V will remain constant. So C can be written as C1 plus C2 plus C3 and so on. So here also you can see the total energy would be half C1 V square, C2 V square, C3 V square and so on. Or in other words, we can say in this case also, in this combination also, in parallel combination, the total energy is what? This is the simply sum of the energies of the individual capacitors. So in both of the cases, whether it is the parallel combination or series combination, in both of the combinations, the energy is going to get added up of individual capacitor to give you the total energy of the combination. Now the next topic is loss of energy. So this was very important topic. Loss of energy on sharing the charges between the capacitors in parallel combination. For example, you are having two capacitors having the different capacitances C1 and C2. Suppose both of the capacitances, they have the different charges or different potentials. Then you see when you're going to combine both of the capacitors in parallel, then Because of the potential differences, the charge will start flowing from higher to lower potential. Then during the flow of the charges through the wire by which you have connected both of the capacitors, some of the energy of the capacitors is going to get lost in the form of heat when the charges are flowing through the wires. So how much that loss is taking place when you are combining two capacitors in parallel. In this topic, we will see what is the loss of the energy when we are combining the two capacitors in parallel and the charge is being shared between them. So let us consider we have the two capacitors having the capacitances C1, C2, and let us consider their charges are Q1, Q2 and their potentials are V1, V2. Total charge after shearing must be equal to total charge before shearing. So this is as per the conservation of the charges. So total charge before shearing and after shearing. You see, when the charges are going to get sheared between the two capacitors, and you see the capacitors are in parallel, so the potential will become equal after sharing of the charges. So the potential is going to become equal, so charges on each capacitor would be capacitance into the potential. So after sharing, potential is same, so it would be C1 into V plus C2 into V, or simply C1 plus C2 into V. But before shearing, both of the capacitors, they have the different values of the potential. So the total charge on first capacitor is C1 into V1, and on the second capacitor it is C2 into V2. So before and after sharing charges, the total charge will remain constant. So you see, using this concept, we have calculated the common potential which both of the capacitors are going to have when the charges are being shared between the two capacitors. So this is the expression of the common potential the two capacitors they have acquired after sharing the charges. So this is the common potential. This is C1 V1 plus C2 V2 over C1 plus C2. Now we can write down the energies before sharing and after sharing of the charges. You see, before sharing, the energy is what? This is half C1 V1 square, because potentials are different before sharing of the charges. Half C1 V1 square plus half C2 V2 square. But after sharing, the potential is going to get same. So after sharing, the total energy is what? This is half C1 V square plus C2 V square, or simply this is C1 plus C2 into V square. So if you will subtract these two values, initial minus final, as we are expecting that final energy is going to get lost in the form of the heat. So final energy will become less. So we are finding initial energy minus final energy. So you're going to subtract these two values here. Initial energy is half C1 V1 square, half C2 V2 square, and final is half C1 plus C2 V square. So you can substitute the value of V. Common potential, we know that this is what? This is C1 V1 plus C2 V2 over C1 plus C2. So substitute this value here in this expression and then subtract both of these values, and little bit simplification will give you this value of the difference in the energies before sharing of the charges and after sharing of the charges. Now you can see here C1 C2 and the C1 C2, they have the positive value. V1 minus V2, whichever is greater, because it is a square here, so this term is a positive term here. So you can see here Ui minus Uf, this is initial energy minus final energy, is greater than 0. So initial energy is more than the final energy, means the energy has been lost. So therefore there is some loss of energy when two charged capacitors are connected together. The loss of energy appears as heat, and the wire connecting the two capacitors may become hot. So when the two capacitors are going to get connected, the charges, they will start flowing from higher potential to lower potential, and we know that the flow of charge in a wire is equivalent to current, so heat will be produced. The wire through which you have connected the two capacitors, they will become hot. So loss of energy will take place. So loss of energy formula we have derived. So that's all for this topic. Thank you.